In this lesson, we're going to continue our study about hypothesis testing with means. So first, we're going to talk about testing hypotheses about paired data. So remember that paired data is used to describe data that are collected in natural pairs. So things that are, say, before and after measurements are good candidates. Maybe you have something about mother's daughters. Or maybe you even have twins, and you're doing twin 1 and twin 2, and you're comparing how, say, a drug acts on these twins. Who knows? Perhaps that's possible. It could also be a matched pair design, in which participants are paired, and one unit in each pair receives treatment. So people could be paired based on some characteristic, such as, say, age. We talked about an example with that earlier in the class that we were doing a memory test, and we paired participants based on age so that age didn't end up being a confounding variable, maybe based on strength, or maybe if you're doing a drug study, severity of the disease. So if you're testing, say, some kind of cancer drug, you want people that are a stage 1 paired with a stage 1, a stage 2 paired with a stage 2, etc. So yeah, we also already discussed before and after. You can collect measurements before and after some treatment, so before or after a diet, or you could record performance on a college entrance exam for each individual before and after a training program designed to boost their performance. And for this situation, essentially, we're going to do a one-sample t-test like the previous section. The only difference is in the pre-processing of the data, you are averaging the differences, not the individual data itself. So the first thing you do, I'm going to say, is you find what I'm going to call the D sub i's, which are the differences. And then you work with those. And just to be clear that we're working with differences, we're just going to give that mu a little subscript of D. So the null hypothesis will be that usually that their difference is 0, as in there is no difference. And alternatively, it will be that either, well, this difference is positive, or it's negative, or it's just not equal to 0 if you have no preference as to what direction it goes. So after figuring out your hypotheses, you summarize the data into an appropriate test statistic after first verifying the necessary data conditions are met. So basically, this is n bigger than or equal to 30 if possible, but lots of the stuff you're going to do in this class won't actually even meet that. So yeah, so before proceeding with the step, find the differences d sub I for each pair. Then verify that n is large enough so there's no extreme skewness or outliers. Compute the sample mean, which we're going to call d bar, and the sample standard deviation, which we're going to call s sub d. And remember that the t statistic is this sample mean minus the null value over the standard error of your sample mean. In this case, that's d bar. So this will be d bar minus a null value of 0 over the standard error of d bar, or d bar minus 0 over s sub d over root n. Find the p-value using the table A.3 or Excel. And then steps 4 and 5 really could be combined into one. Decide whether to reject your null hypothesis or not, and then report the conclusion. Okay, give the value of the test statistic t and the p-value or p-value range for this situation. So the null alternative hypotheses are already done for us. So there's step 1. Okay, find the test statistic, which is step 2. T equals d bar minus 0 over standard error of d bar, which is d bar minus 0 over s sub d over root n. So that is -4 minus 0 over 15 over root 60. Well, this comes out to be about negative 2.066, which we're going to round to about negative 2.07. Okay, find the p-value. So observe that this is a two-sided test because mu d is not equal to 0 is what HA says. So our p-value is going to be the probability that we're either lower than negative 2.07 or bigger than positive 2.07. And which you can see from the picture is twice the probability that t is less than or equal to negative 2.07. So that's 2 times, well, in Excel this would be t dot dist negative 2.07. Ooh, degrees of freedom. That would be 59. And this comes out to be 2 times 0.0214 or 0.0428. So that's the exact p-value using Excel. You do also have to know how to do this using the table. So let's talk about how to use the table. Okay, so looking at your table, so first of all, we want to find the probability that t is bigger than or equal to 2.07. And notice, and we have degrees of freedom equal to 59. Well, that's not on our table, but it's close enough to 60. Let's just go with 60. So about equal to 60. Okay, so you have that your t-value 2.07 is in between 0.0 is between 2 and 2.0. So t equals 2.0 and t equals 2.33. Okay, and your p-value is twice that number. So p is in between those. And now look at who's the smaller one. The smaller one's 0.012. So 0.012 on the bottom, 2 times that. And on top, 2 times 0.025. Remember that the alligators eat the biggest number. They're hungry alligators. Sorry, cheesy explanation. 0.024 less than p less than 0.05. That would be the p-value range that you got from the table. If you wanted to be even more conservative, you could have used degrees of freedom equal to 50, but that wouldn't have actually changed the result because the values there are the same. So, not needed. Okay, and also remember that this 0.05, that comes from the t-value of 2.0, and this 0.012 comes from 2.33. And so since 2.07 is closer to 2.0, it makes sense that the p-value is like closer to this side of the interval as opposed to that side. So this is the never-ending question. Most people complain that they gain weight during the December holidays, and Yanovsky, among others, wanted to determine if this is the case. They sampled the weights of 195 adults in mid-November, which apparently is when you're at your lowest weight before Thanksgiving, and again in early to mid-January. The mean weight change for the sample was a gain of 0.37 kilograms, with a standard deviation of 1.52 kilograms. So state and test the appropriate hypotheses. We're going to use alpha equal to 0.01 instead of 0.05. Okay, so first thing, well, we're testing the hypothesis. Let's say H naught is that the differences in before and after weights is 0. So no difference in, let's figure out which one's going to be higher. I'm going to say after minus before. And the reason after minus before is if there was a weight gain of 0.037, that means that the after weight was larger. So after minus before is going to be the positive quantity. Okay, HA, mu D is in this case positive. So we're testing that the after weight is greater than the before, or saying that weight gain happens. Okay. Second is to find the test statistic, which is a t statistic, so clearly state that. T is d bar minus 0 over standard error of d bar, or d bar minus 0 over s sub d over root n. Okay, well in this case, the d bar was 0.37 kilograms over s sub d, which was 1.52, root 195. So this comes out to be 3.399. So rounding to 2 decimal places, t really is about equal to 3.40. Okay. So step 3 is to get the p-value. So p is the probability that t is bigger than or equal to 3.4. And if you're using Excel, you have to go the other direction. Probability t less than or equal to negative 3.4. Which is equal to t dot dist negative 3.4, 194 degrees of freedom, 1, which should give you 0.000409 approximately. Now using your table, in case this was Excel, using table 8.3, degrees of freedom equal to 100 is the closest. And you see that looking across that probability t bigger than or equal to 3.4, well 3.0 is the biggest t statistic on there. This is going to be less than 0.02. So, in any case, p is less than that, p is equal to this exactly. Steps 4 and 5 are to make a conclusion. And we were asked to use alpha equals 0.01 instead of 0.05. So as your p is less than 0.01, you can reject h naught and accept HA. Weight gain is real. People do gain weight over the holidays. At least on average they do. Some people, some lucky few, don't. But the average person definitely does. Do you find going to the dentist stressful? It's like a test you haven't studied for 6 months. Have you brushed your teeth or not? Have you flossed enough or not? Okay, but seriously, many people do have high anxiety about visiting the dentist. And researchers want to know if this affects blood pressure in such a way that the mean blood pressure while waiting to see the dentist is higher than it is an hour after your visit. So is the before blood pressure higher because you're nervous than after, when hopefully you've had no cavities or no serious issues and you can go home and move on? So 10 individuals have their systolic blood pressure measured while they're waiting in the dentist room, and again an hour after the conclusion of the visit. And the data are as follows. So the first thing, write a parameter of interest in the situation. So what we care about is mu sub d, which is the mean difference in blood pressure waiting to see the dentist and 1 hour after. Okay, write null and alternative hypotheses. So H naught is that difference is 0. So no difference in before and after blood pressure. HA is specifically that the before is higher, so I'm going to say this is positive, and we'll say BP is higher before. Part C says to find the remaining steps to test the hypothesis. And before we do that, to do step 2, we're going to have to find the average of the differences and the standard deviation of the differences. And I'd like you to do these using technology, not by hand, because it's really tedious. And before we can do either of those, we have to find the differences. So there's no space on here, but there's a space on your note sheet. I'm going to say D sub I for differences. I'm just going to write them above, but you can write them below. We're going to do before minus after. So 132 minus 118 is 14. 135 minus 137 is -2. 149 minus 140 is 9. This next one's -6. Next one is 12. Next is 5, 6, 8, 4, and 7. And there are a few people you can see, this person and this person actually had lower blood pressures before. Maybe this person needed a root canal, but almost everybody else had a positive value, which meant the blood pressure was higher before than after. Now, what I did to calculate D bar and SD was I entered these things into Excel. So these 10 differences. So put the D sub i's into Excel. And then D bar will equal, you type in average, and then just highlight the column, which will go 1 through 10, A1 through A10 or whatever. And it should give you 5.7. And it's not a bad skill to know how to use Excel to do some of this stuff, so make sure you can figure that out. SD, which is the standard deviation, you type in STDev and highlight the column 1 through 10, and this should give you 6.019. If it was a test, obviously I'm going to give you these questions because you can't use Excel. Okay, our test statistic T is D bar minus 0 over standard error of D bar, or D bar minus 0 over S sub D over root N. So that's 5.7 minus 0 over 6.019 over root 10, which comes out to be about 2.99. Okay, step 3 is to get that p-value. So the degrees of freedom is equal to 9, and by golly, this is close enough to t equals 3. We're just going to use t equals 3. 6, 7, 8, 9. So our p-value is the probability that our t statistic is bigger than or equal to 2.99, which is about equal to 0.007. Okay, step 4 and 5. So since this p-value is less than our alpha, which is usually 0.05, so since p is less than 0.05, we're going to reject h0, accept ha, and it says that the blood pressure after a visit is lower than before, or you could say the blood pressure before a visit to the dentist, before a visit to the dentist is higher than 1 hour after, on average. All right, next we're going to move on to the final hypothesis test, is testing hypothesis about the difference in two population means of independent samples. So in this case, we want to test whether the means of populations represented by two independent samples of a quantitative variable differ. The two populations may be two different categories, say like men and women, or two groups who receive different treatment groups in an experiment, say a drug group and a placebo group. So this procedure is called the two-sample t-test, or a t-test for the difference in two means. And the first thing you have to be able to do is tell this apart from the paired differences thing. So for each of the following situations, identify whether the appropriate test is a paired t-test, as in previous section, or a two-sample t-test. So the weights of a sample of 15 marathon runners were taken before and after a training run to test whether a marathon runner lose dangerous levels of fluids during a run. So is there a natural pairing? Yes or no? Well, same marathon runner before and after, so yes. This is paired data. Natural pairing is a before and after. So this is a paired t-test is the appropriate procedure. Random samples of 200 new freshmen and 200 new transfer students at a university were given 50-question test on current events to test whether the level of knowledge differs for new freshmen and transfer students. So unless these freshmen are all siblings with those transfer students, there's no natural pairing. Two independent groups. So this is a two-sample t-test. Don't need all those dashes. So two-sample t-test. And just to be clear here, the parameter here is mu sub d, like this is your null hypothesis we'll talk about. The parameter in this case is mu1 minus mu2, so the difference in the means of these two populations. All right, now we have two cases, much like we did for the confidence intervals. So the unpooled procedure, so the difference in this case, the difference is, in this case, the two sample standard deviations are assumed to be different. And we should really say different in quotes because they're probably often going to be different, but if they're very different. Very can be hard to quantify. You're going to use this to find the standard error. And in this case, the degrees of freedom is equal to the smallest of your N1, N2, take away 1. And you can also sometimes pool the standard deviations together if they're equal, and I'll say equal in quotes again because they'll be close to equal. You can use the pooled two-sample test, which is based on the fact that the true sample standard deviations are equal. And you kind of do a weighted average of sorts by putting these things together. And then once you've calculated this SP squared, you use that in this formula, which is the same as the formula above, except for you see how this is SP and this is SP, whereas this is S1 and that's S2. And the nice thing for this one is that the degrees of freedom is equal to N1 plus N2 minus 2. And bigger degrees of freedom also leads to smaller p-values given the same t-statistic, so that's one reason why that's a little bit important. And of course the question is how do you choose which test? What could you use to show that the standard deviations of two samples are approximately equal? And when do you pick? So first of all, let's just review that you use unpooled if standard deviations are not the same, and you use pooled if the standard deviations are the same. Okay, so some things that you could use to show these standard deviations are equal. First thing you could do is you could compare the sample standard deviations. So compare S1 and S2. If they're close, use the pooled procedure. If not, use the unpooled. But close, how close is close enough? That's a little bit up to debate, right? It's not necessarily there's a hard, fast line as to which is right. So if they're close together. And you could also use graphical stuff to confirm your data, because notice this is affected by sample size. And if you have drastically different sample sizes, the standard deviation corresponding to the bigger sample will probably be lower because that involves dividing by n, or dividing by n minus 1. So just be aware of that. Thing two you could use box plots or histograms to compare the spread of your data. Because that's kind of what standard deviations measure. They measure spread. So if the spread is sort of somewhat similar-ish, then maybe you can use the pooled procedure. If the spread's not similar, you can use the unpooled. So we'll do two more examples, one using the unpooled procedure and one using the pooled procedure. All right. In a study, sedentary men were randomly assigned to be placed on a diet or exercise for a year to lose weight. 42 men were placed on a diet, so there's one of our sample sizes, and the remaining 47 were put onto an exercise routine. The group on a diet lost an average of 7.2 kilograms with a standard deviation of 3.7 kilograms. That's quite a bit of weight, actually. The men who exercised lost an average of 4 kilograms with a standard deviation of 3.9. So decide whether to use a pooled or unpooled test. Explain your reasoning. And I'm going to say that since these standard deviations are pretty close together, I'm going to use the pooled procedure. So use the pooled procedure as I'm going to call it S1, which is equal to 3.7, is about equal to S2, which is 3.9. Or let's say the sample standard deviations are approximately equal. All right, state your hypotheses in words and using proper mathematical symbols and notations. And the question doesn't specify that one regime is better than the other, so I think that means that HA will be a not equal to, unless it explicitly says greater than or less than or more or less. Don't assume a direction. So H naught will be that the mean weight loss for one group is equal to the mean weight loss for the other, or mu1 minus mu2 equals 0. So mean weight loss is the same for both diet and exercise. And HA will be that mu1 is not equal to mu2, or mu1 minus mu2 is not equal to 0, or the mean weight loss is different for diet and exercise. All right, find your test statistic. So since we did the pooled procedure, the first thing we have to do is find SP squared, which is equal to N1 minus 1 times S1 squared plus N2 minus 1 S2 squared all over N1 plus N2 minus 2. So that's 42 minus 1 times 3.7 squared plus 47 minus 1 times 3.9 squared all over 42 plus 47 minus 2, and parentheses. If you're going to do this in one go, make sure you put a parenthesis there and a parenthesis there. So punch this in your calculator and you should get SP squared is about equal to 14.4937. Okay, and then next I'm going to find the standard error of x1 bar minus x2 bar. And since we're using the pooled case, this is SP squared over N1 plus SP squared over N2. So that's the 14.4937 over N1, which is 42, plus 14.4937 over 47. It's about equal to 0.80837. A lot of you have been asking me about how to round, how many decimal places to keep, because I'm definitely not consistent. And when I do my calculations in my calculator, there's a feature that lets me use this thing as the previous answer. So when I type this thing in a calculator, I'm going to type in my square root, my parenthesis, and then I'll type in this ANS, which on my calculator is a little button that you can select. It's the negative sign, second negative sign. Everybody else's is different, but you can do ANS divided by 42 plus ANS divided by 47, close your parenthesis. And that will make sure that you never have an error due to rounding. It also saves you time because in my case pushing second and then the minus sign is what it takes to get that. And that's a lot less typing than typing in 14.4937 repeatedly. So go ahead and give it a try. The calculator that I use is a TI-30X, because it's a really simple thing, but any TI, Texas Instrument calculator, will have a similar feature. Casios and your iPhones are a little bit stupid. They don't seem to do things, and you have to really know what you're doing to do it right, and it makes it a little bit harder. Okay, moving on. We're not quite done yet. Holy moly, so sorry. Test statistic. Geez. T is equal to x1 bar minus x2 bar minus the null value of mu1 minus mu2 is 0 over the standard error of x1 bar minus x2 bar. So that's 7.2 minus 4 minus 0 over that 0.80837 that I found. And I got that t was equal to 3.959 or 3.96. You can also use that whole answer feature again when doing this. All right, next find the p-value. So in our case, the degrees of freedom is 42 plus 47 minus 2, which is 87. P is 2 times, because of two-tailed, probability our t statistic is bigger than or equal to, more extreme than what we found. We'll say 3.959. Which is, to use Excel, we have to go less than or equal to. So 2 times probability t is less than or equal to negative 3.959, which is 2 times 0.123477, super small number, or about equal to 0.00015. That's a very, very small p-value. Using table 8.3, well, we have degrees of freedom is about 80, maybe about 90. And the t we have is bigger than 3. So our p-value is less than 2 times the p-value, which corresponds to t equal 3. And for degrees of freedom equals 80, that's less than 2 times 0.002. which implies that p is less than 0.004. And even if we don't know what p is exactly, knowing that it's less than 0.004 is enough to conclude statistical significance. And you do see that these two things make sense. Less than 0.004, 0.00015 certainly meets that. All right, state your conclusion in context. Well, we're going to reject H naught. And we're going to accept HA, and we're going to say that the weight loss between, or the weight loss difference between diet and exercise, how do I say, the weight loss between diet and exercise, take out the difference. Diet and exercise is different on average. You can probably even venture to say that it seems to be higher with the diet. All right, one more. Between 1954 and 2003, 42 different swimmers have crossed Lake Ontario. Both men and women have made the crossing. For the 22 women, the average time is 1,271.6 and a standard deviation of 261 minutes. For the 20 males, X bar is equal to 1,196.8 minutes and S is 304.4. Box plots of the two data showed symmetric distributions with very different spreads. We're going to use women minus men in this case. Okay, decide whether to use a pooled or unpooled test. And I told you, underlined in black, which one. You see the words very different spreads? That means that the standard deviations are different. And also you can see 261, 304.4, yeah, not very close together. So we're going to use unpooled. as the problem states, the spreads, which would be the standard deviation, are different. Okay, state your hypotheses in words and using proper mathematical symbols and notation. All right, so H naught, well, we're going to say that the mean time for men minus mean time for women is 0. So this would be the mean swim times are the same for both genders. And just because I want to do an example of a one-sided test, let's propose that the men are faster. mu1 minus mu2 is bigger than 0. Mean swim times for women are slower. And remember that in this is like golf, faster is better. That means this is a bigger number than this. All right, find your test statistic. So standard error of x1 bar minus x2 bar, since we're using the unpooled procedure, this is s1 squared over n1 plus s2 squared over n2, which in our case is, well, s1 is 261 over 22 plus 304.4 squared over 20. This comes out to be 87.9169. Now our test statistic is a t. This will be x1 bar minus x2 bar minus the null value, which is 0, over standard error of x1 bar minus x2 bar. All right, so women's time is 1,271.6 minus 1,196.8 over 87.9169. And that comes out to be about 0.851. All right, find the p-value. Well, in this case, for degrees of freedom, we use the smallest of the sample sizes. So 22 women, 20 males, so 20 is smaller. 19. So p is the probability that our test statistic is bigger than or equal to 0.851. Using Excel, probability t is less than or equal to negative 0.851, which comes out to be 0.203. And using your table, there is a df equals 19 row, but the closest t statistic you have is t equal to 1.28. So your p-value is to the left of that, which means your p is bigger than 0.108. That's all the information you could glean from the table. And does that match the Excel value? Yes, it does. Okay, so state your conclusion in context. Well, we are going to fail to reject H naught. And there is insufficient evidence to conclude that men swim faster than women on average when crossing Lake Ontario. There is insufficient evidence to conclude that men swim faster than women when crossing Lake Ontario. So at this stage, you'll have done every single kind of confidence interval you're going to see and every single kind of hypothesis test you're going to see. And you've done 95% of what is in this course. So good job.